Moving into section 4.3, and now we're getting into this is kind of the middle section of the chapter, so we'll be at the halfway point after today. So, a lot of things in 4.3 are very descriptive in nature or visual in nature. So, I want to start by just kind of talking over some terminology, kind of boring stuff. So, it's kind of nice to get this stuff out of the way in video format. So first of all, we've spent the last few days doing Riemann sums, which we saw were a way to accumulate the area under a curve by splitting it up either into rectangles or trapezoids of different widths and different number of rectangles and trapezoids. And Riemann, he gets credit in calculus not just for doing that, because that's not anything super exciting, but what he really gets credit for is the idea that he transitioned that idea to integration and realized that you could actually, by using calculus and integration, you could figure out an exact area under the curve by accumulating those rectangles. Essentially, he thought of it as like a limit where the number of rectangles became infinite. If you had an infinite number of rectangles and you added them all together, they would obviously get skinnier and skinnier and skinnier, but you could get an answer that would give you a perfect approximation of the area under the curve. So that's kind of the connection with Riemann and where he goes with integration. So this first definition, which you're probably looking at going, what in the world is going on? I just want to kind of explain it in very basic terms. You'll never have to actually write out anything like this, but it is the idea that your number of rectangles, which is your n, or your number of partitions, the idea is you want that to go to infinity, and then you want to accumulate or take the summation of all of those rectangles. So that's why you see that little summation symbol from 1 to n. And by doing that, you're going to take your length times width. So your f of c sub I is the height of each rectangle. And then your delta x, that's how wide each rectangle is. Obviously, they keep getting skinnier and skinnier and going to 0. And if we took the summation, all of that, we would eventually get the exact area under the curve. So the connection that he made is we can actually write that, and you've already seen that in some of the problems we've done, as an integral where you have boundary numbers at the bottom and top, which is saying where are we slicing this into rectangles from A to B. So that's kind of the connection between integration and Riemann sums. So everything we did in section 4.1 was called an indefinite integral. Indefinite integral means that when you integrate, you get an answer that's still in terms of x. We call it a family of functions. Our switch now is to look at something called a definite integral. So in 4.3, the focus is all definite integrals. This is when you actually get a numerical answer, and you'll notice the integration symbol has numbers below and above it. We call those the boundary numbers or the limit numbers. A, the lower number, is your lower boundary or limit of integration, essentially where you start. And then B is your upper boundary or upper limit of integration, which again is kind of where you end this slicing it into rectangles. So when we talk about area, we can always represent area as a definite integral from A to B. Where do we start and where do we end? And then having our function f of x, which is what bounds it on the top. So we're going to start with really simple like geometric problems and talk about what does this look like? How do we create this? And then we'll move to ones that aren't quite as geometric and are more focused on some kind of more abstract areas. So we do have a theorem that says as long as a function is continuous on an interval, then it is also integrable, meaning we can always do this process as long as we don't have a discontinuity in our interval. Now, you may have something that you don't know how to integrate because we have just scratched the surface of what you know how. That doesn't mean it's not integrable yet. It just means that maybe we aren't to the point where we know how to do it. It can be done just eventually with other knowledge. So looking at a few here, what I want to do here is take a look at what happens if they give you a definite integral that would create a geometric shape that you know how to work with. How do we find our answer using geometry instead of calculus? So this first one, number 1, is the integral from 1 to 3. So that are your boundaries of integration. So that's 1 to 3. And then your function that's on top of it is 4, which is your just a horizontal line y equals 4. That definite integral creates this picture that you see down here. I tried to draw the pictures perfectly so you didn't have to worry about my horrible artwork. I can actually get an answer by just using geometry. I know that it's a rectangle. I know rectangle's length times width. So it's 2 wide, it's 4 high. So my answer is 8. Definite integrals, again, give a numeric answer, not an answer with variables still in it. The next one is the integral from 3 to 6. So again, those are my start and my stop. And then my function is y equals 4x plus 1, which is just a line that has a slope of 4. And it creates a trapezoid. Well, we know how to find area of the trapezoid. It is 1/2 the height times the bases added together. So my height is just going to be my distance between my boundary numbers. So my height is 3. My bases are going to be found by putting the 3 and the 6 into my function. You don't want to count. Obviously, I made this scale, so you're not going to be able to sit there and go 1, 2, 3, 4 and see how high it goes. But we have an exact way to do it. We're going to put 3 into my function. When I do that, I get 13. And then we're going to put 6 into my function, and I'm going to get 25. So then I'm going to either do it in my head, do a calculator. Let's see, 13 plus 25 is 38. Half of 38 is 19. 19 times 3 is 57. We don't usually put units on our answer, but in something like this, we would say it's square units because it is indicating an area. 2 more. So the next one, we are going from 0 to 6. We are looking at the function x over 2, which is just the same thing as 1/2 x. So it's just a function that has a slope of a half. And you'll notice that when I do this, the area that ends up bounded is a triangle. So triangle 1/2 base times height. Anytime you're asked to do something like this that's very geometric, you're going to stick with very basic geometry shapes. So my base is 6 because it goes from 0 to 6. And my height is going to be what I get when I put 6 into my function. So when I put 6 into my function, I get a height of 3. So half of 18 is 9. And then finally, this next one, it creates a semicircle. So when I take the square root of a number minus x squared, it is going to be a semicircle. I know it looks kind of distorted on my graph. The radius of that center semicircle will be the square root of whatever this first number is. So it does have a radius of 2. We are going from -2 to +2, so we are getting this whole part that's on top. So area of a circle is pi r squared. Now realize it is a semicircle, so I do want to cut my answer in half. My radius is 2, so I do pi times 2 squared, which gives me 4 pi, and then I cut it in half because I only want the top part, so my area is 2 pi square units, and I'm not going to worry about a decimal. I think 2 pi is a lot easier to work with. So that gives you a basic introduction of how definite integrals can be drawn and understood as a visual picture, and how we can use geometry to help us find area.